Greetings friends, welcome to our channel CodeChef. If you want to learn competitive programming or you want to master data structures and algorithms, then this is the right place for you to be at. Every week we upload CodeChef contest video tutorials and videos on various important data structures and algorithms. If you are new to the channel, subscribe to the channel and turn on the notifications. In the last video we saw how the greedy approaches are used to solve a few optimization problems, and we also came up with the solution for a few optimization problems. But how do we know whether our solution was correct or wrong? It might be the case that our solution looks correct but is actually wrong. So we need to prove whether our solution is right or wrong. And one such method that can be used in order to prove whether a greedy solution is right or wrong is called as argument exchange. So this video we are going to talk about this method, argument exchange. Argument exchange. The idea of argument exchange is to continuously modify our so-called optimum solution into a solution that is produced by our greedy algorithm. And in the way of our modifying, we also make sure that we don't worsen the solution's quality. Thus, the quality of our greedy solution is surely going to be at least as great as the quality of the optimum solution. I'll explain this in simple words. So while trying to prove a greedy algorithm using exchange argument technique, what we do is we assume that there exists some optimum solution which is not same as our greedy solution. Now what we do is we try to convert our optimum solution into a greedy solution in small steps. That is, in each move we are going to convert a very small part of our optimum solution such that it looks like our greedy solution. But while making that transition, we'll also make sure that the new solution that we are going to get by changing the optimum solution is surely going to be as good as the solution we already had, if not better. In other words, we will have some optimum solution and we are going to slowly convert it to a greedy solution, but in the way that we have converted our greedy solution, we have never degraded our optimum solution. And if we have not degraded our optimum solution, then this indirectly means that the greedy solution is very equivalent to the optimum solution. So we'll start by taking a very simple example but yet very useful example. So consider that there are two numbers a and b such that the sum of those two numbers turns out to be n, which is an even number. Now what we have to do is we have to choose a and b in such a way that the sum is still n but the value a into b value is getting maximized. So this is an optimization problem because you need to maximize something. And there are also a few constraints in this problem. The constraints are that a plus b should be equal to n. So not every value of a comma b is going to be feasible. There are some set of a comma b values which are going to be feasible. And among all those set, there will be only one value which will be our optimum solution because that one value will maximize our a into b value. So let us come up with a greedy solution. Firstly, I will come up with a greedy solution such that the a and b value that we are going to choose should be as close as each other. In other words, if n is even, then our greedy algorithm would be that a should be equal to n by 2 and b should be equal to n by 2. And this is a feasible solution because a plus b is still n. And what will our a into b value be? Our a into b value will be n squared by 4. So according to my greedy solution, I'll always split a and b in such a way that a is equal to n by 2 and b is equal to n by 2. But I have not yet proved that my solution is correct. For that we are going to use exchange argument technique. So according to my solution, the greedy approach gives me the answer of n squared by 4. Let us consider that we have an optimum solution a comma b, and let us assume that a is lesser than b. We can do this because we can maintain the generality. Now if a is lesser than b, it's for sure that a is going to be less than n by 2 and b is going to be greater than n by 2. Now let me assume that I am going to write a as n by 2 minus delta and b as n by 2 plus delta. I am assuming that this a and this b is going to be my optimum solution, and this is not the same as our greedy solution. Now, what will a into b value be for this case? The a into b value is going to be n by 2 minus delta times n by 2 plus delta, which is n squared by 4 minus delta squared. So our optimum solution gives us a value n squared by 4 minus delta squared. Now what I am going to do is, I am going to exchange my optimum solution by my greedy solution. In other words, my optimum solution was n by 2 minus delta and n by 2 plus delta. Now I am going to exchange it by n by 2 comma n by 2. And after exchanging, I am going to check how this exchange will affect my result. So when I make this exchange, I am going to get my a into b value as n squared by 4. Now one thing that I can clearly see is that n squared by 4 is surely going to be greater than or equal to n squared by 4 minus delta square. This is the solution that I am getting from my greedy approach, and this is the solution that I am getting from my optimum approach. Now I have proved by converting my optimum solution to my greedy solution, for sure I am not going to worsen my solution. In fact, there might be the case that I am going to improve my solution, but I am not going to surely worsen my solution. So indirectly I can say that my greedy solution will be the actual optimum solution. Let us try to understand the same approach by now taking proper steps and solving a proper problem. So this is the problem that we are going to look at. We have n sticks and the length of the ith stick is Li units. We need to pair these sticks in pair of 2s such that in any pair that we choose, the difference of the length of those two elements in the pair should be at most d. Now what we need to do is, we need to make the maximum number of such valid pairs. What are valid pairs? Two sticks A and B are said to be in a valid pair only and only if the difference in the length is lesser than or equal to d. Let us take an example and see what are valid pairs and what are not. So consider that we have an array where we have chopsticks of length 1, 3, 3, 5 and 7. And the value of d, which means the parameter which is used over here, is equal to 2. In that case, pairing these two chopsticks is valid because the difference in the length is lesser than or equal to d. But pairing these two chopsticks would not be valid because the difference in the length is going to be greater than 2. Similarly, pairing these two chopsticks is valid because the difference is lesser than or equal to 2. But pairing these two chopsticks is going to be invalid. So in other words, we need to make valid pairings, but not only we have to make valid pairings, but we have to make the maximum number of pairings possible. So first we are going to come up with a greedy algorithm. But how do we come up with a greedy algorithm so fastly? Coming up with a greedy algorithm can only become easier for us with the help of practice and by solving more and more problems of the same type. Because when we see a problem which can be related to a previous problem, we can very easily take the same greedy approach and modify it to get the right greedy approach for this problem. So getting the right greedy approach can only be done with the help of practice and having good intuition. For this problem, let us try a greedy approach. And what greedy approach we are going to try is that we are in each step, what we are going to do is, we are going to pair the minimum element with the second minimum element. And if this pairing would be valid, then we are surely going to pair them up. But if this pairing is not going to be valid, then we are going to consider that the minimum element cannot be paired with any other chopstick, so we are going to discard it. So this is our greedy approach. But we don't know whether this greedy approach is right or wrong. It might be the case that this greedy approach might be wrong. But we need to prove that this greedy approach is right. Let us try to have a look how this greedy approach can give us a solution for the example that we took over here. So what we are going to do is, in each step we are going to find the element which is the minimum element and the element which is the second minimum element. In this case, 1 is the minimum and 3 is the second minimum element. Now we are going to check whether this pairing is valid or not. 1 and 3. Yes, the pairing is valid because the difference is lesser than or equal to 2. So what we are going to do, we are going to pair them up. So now we have a pair ready which is 1, 3. Next, again in the remaining array, we are going to find which is the minimum element and which is the second minimum element. In this case, min is 3 and second min is 5. Again, these two are in a valid pair because 5 minus 3 is equal to 2, which is lesser than or equal to 2. So we can again pair 3 and 5. Then we are left with only one element, and since this one element cannot be paired, so we are not going to do anything. So our greedy approach says that at max there can be only 2 pairing for this given array, which is actually correct. So looking at this particular example, we feel that our greedy solution is right. But this thing does not guarantee us that our solution is right. Now we will have a look at how we can use the exchange argument technique in specific to prove that our solution was right. So these are the steps that are used in order to prove whether the solution that we get from our greedy algorithm is same as the optimum solution. So what are the steps? Step 1. Label your algorithm solution and the general solution. So let me say that the algorithm solution, that is the greedy algorithm solution that I am going to have, will be called as G. And the general algorithm solution, which means the solution which is considered to be an optimum solution, I will call it O. And these are the solution for the problem that are given to us. Now we will read the second step. Compare the greedy solution with the optimal solution or the other solution. So if there is any difference in the greedy solution and optimum solution, then we will continue with the next step. But if there is no difference between the greedy solution and the optimum solution, so indirectly we have proved that our greedy solution is the optimum solution, and so we can stop processing, and we have proved that the greedy solution is indeed correct. But in case there is a difference between the greedy solution and the other solution, what are we going to do? So in case there is a difference, we are going to make a small exchange. What do I mean by exchange? We are going to replace a very small part of our so-called optimum solution by our greedy solution. And when we make that swap or when we make that exchange, we also make sure that the solution that we have got now, the solution that we have got after the exchange, is no worse than the solution before. That is, this swap that we have made or this exchange that we have made has not worsened our solution. So after making the swap also, the solution that we have had is still optimal. So using this approach, we are going to slowly convert the optimum solution that we initially had into the greedy solution. And since in every step we are making sure that the new solution that we got is still a valid and an optimum solution, so we have indirectly proved that the final solution that we are going to have, which will be greedy solution, is going to be an optimum solution. And hence we have proved that our greedy algorithm was correct. Let us try to apply these 3 steps for the problem we have. So what we are going to do is, we are going to follow all the given steps. What was the first step? We have to label a solution as our greedy solution and one solution as the optimum solution. So we will consider a few cases. So consider that L1 cannot be paired with L2. In that case, I will first prove that L1 cannot be paired with anything else. So what I am stating is, if L1 and L2 pairing is not possible, then L1 and L3 pairing is also not possible, and L1 and L4 pairing is also not possible. So in other words, what I am stating is, if in our greedy solution L1 is unpaired, then in any optimum solution also L1 will remain unpaired. How can I prove that? Let me assume that L1 and L2 have a difference of x. Since the difference between L1 and L2 is x and the value of x is greater than d, because we have said that there exists no pairing, and when will pairing not exist? Only and only if this difference is greater than d. So if L1 and L2 has a difference greater than d, then for sure the difference between L1 and L3 is also going to be greater than d, because we know that the difference between L1 and L3 is greater than or equal to the difference between L1 and L2. You can see that because the array is already sorted, and if the adjacent elements have a difference x, then these two non-adjacent elements are surely going to have a difference greater than x. So what I have proved is, if in the greedy solution of ours L1 is unpaired, that is L1 is not paired with L2, then L1 can never be paired. So what did we state? If L1 cannot be paired with L2, we'll discard L1. since L1 can never be paired, so discarding this L1 is optimum for us. Now let us consider some other case such that L1 now can be paired. So now let us consider that in the optimum solution, L1 is not paired with L2. In the greedy solution, L1 is surely paired with L2. But in the optimum solution, L1 is not paired with L2, but rather L1 is paired with L3. And L2 is still unpaired. L2 and L4 are still unpaired. So what I have is L1 and L3 are paired, and that's the only pair that I have. Now what I prove is replacing this solution, that is exchanging this solution by my greedy solution, which is L1, L2 will not worsen my solution. How can I prove that? Since L1 and L3 were already paired, so I surely know that the difference between L1 and L3 is lesser than or equal to D. So I can say that L1 minus L3 minus L1 is lesser than or equal to D. If I know that L3 minus L1 is lesser than or equal to D, then one thing I know for sure, that L2 minus L1 is also going to be lesser than or equal to D. Why? Because we can already see that L3 is farther away from L1 than L2 is. So if L3 itself is less than D distance away, then it's for sure L2 is also going to be less than D distance away. So if L3 and L1 can be paired, so L2 and L1 can also be paired. So if L2 and L1 can be paired, so let me just try to exchange the optimum solution with my greedy solution, which is L1, L2. When I made this exchange, one thing that I made sure was that what was the solution before this exchange? Before this exchange also there was only one pairing, which was L1 and L3. And after this exchange also I proved that there is at least one pairing, L2 and L1. It might be possible that now L3 and L4 can also be paired, but one thing that I made sure is there is at least one pairing. So for sure I am not going to worsen my solution. So making this exchange will not worsen my solution. Now let us consider another case. And this case is that L1 is paired with L3. But now L2 is also paired with L4. So now L1 is paired with L3 and L2 is paired with L4. But what does our greedy algorithm say? According to us, L1 should be paired with L2 and L3 should be paired with L4. But I am stating that optimum solution is L1 being paired with L3 and L2 being paired with L4. Now what can I say is, let me try to exchange this solution by the solution I have, which is let me try to exchange L1, L3 and L2, L4, which will be our O. What is our O? Our O is L1, L3 and L2, L4. Let me try to slowly exchange this O to G, and I'll prove that even after making this small transition from O to G, I am not going to worsen my solution. But for that first I have to prove that my G is still a valid solution. I can say that L1 and L3 are parallel and L2 and L4 are parallel. But I need to prove now that L1 and L2 are also parallel and L3 and L4 are also parallel. So let us try to prove that. This thing can actually be very easily proved, because we can easily see that the difference between L1 and L3 is greater than the difference between L1 and L2. So if the difference between L1 and L3 itself is lesser than or equal to D, then we for sure know that the difference between L1 and L2 is also going to be lesser than or equal to D. So L1 and L2 are surely going to be parallel. And if the difference between L4 and L2 is lesser than or equal to D, because in the optimum solution they were parallel. So if the difference between L4 and L2 is lesser than or equal to D, then why won't the difference between L3 and L4 be lesser than or equal to D? L3 is closer to L4 when compared to L2, right? So the difference between L3 and L4 is for sure lesser than or equal to D. So in our optimum solution we have two pairings, which was L1 with L3 and L2 with L4. This is not a problem. But in the greedy solution we still have two pairing. That is, making this exchange we did not worsen our solution. So after considering the three steps that were given and making sure that making the exchange does not worsen our solution, we can say that our solution for this problem is an optimum solution, and the greedy solution that we are going to make is going to be an optimum solution. So this is how we are going to use exchange argument method to prove our greedy solution. In the future videos we are going to solve difficult but classical problems of greedy algorithm, and after solving those classical problems we are going to dedicate an entire video to prove that our solution for those classical greedy problems was indeed correct, and we are going to prove those solutions by using this method of argument exchange. For this solution, we came up with the optimum solution in our first go, but that's not going to be the case every time. Many times we need to try various different possibilities, various different approaches, and then we can come to our optimum or greedy solution. But before that, when we reach some non-optimal or some incorrect greedy solution, we need to find a way so that we can discard that greedy solution. So it's also an important part that we are able to disprove whether our greedy solution is correct or not. So in the next video, we are going to look at a few tips and tricks that we can use in order to prove whether our solution is incorrect or not. Because if our solution is incorrect, then we won't be wasting our time trying to code that solution and trying to think about that solution. So stay tuned for the next video.